Hello, everyone. Welcome back. Today, we are going to be talking about hybridization, which is a very key role in what we're going to be seeing throughout the rest of the course. So make sure that you take good notes for this one because it's going to be very important. But the first thing that we really need to talk about when we're looking for hybridization is we need to ask ourselves the question, what are orbitals? Because essentially, we've kind of been using them throughout the course so far, but we haven't really touched on what they are. And so now is when we're going to do that. And the first thing we need to think about is let's think about carbon for a second, right? Carbon, our little friend here, we talked about it a long while ago, having these four valence electrons, right? And very simply from lecture one, we said that if you take that alongside four of these hydrogens with one valence electron, you're going to end up with a situation where you have the carbon with all four hydrogens hanging out around it, bonded like so. But we never really talked about how that happens. And so to understand how that happens, we have to answer this question of what are orbitals. And we have two different orbitals that we're going to focus on in this class. There are more as you go down the periodic table, but the most important ones to us are these s orbitals and these p orbitals. And so there's two different types of orbitals here, this s and this p. And quite simply, they come from just where the electrons sit around the nucleus. And so s orbitals are very simple. They are just plain old circles, right? They are circular, which means that the electrons can be in any direction. Whereas the p orbitals that we look at are a little different. These ones are split into three different directions, right? And so these are distinct in the fact that we have one that is in the x direction, one that is in the y direction, and one that is in the z direction. And so what we're thinking about here is if we just look at one of these 3D plot maps, right? This would be our, well, I guess normally people would call this y, people would call this x, people would call that z. The Z1, keep in mind, this is technically going in and out of the page. All right. So that is the three different p orbitals that we have. A px, a py, and a pz. And the thing is, all atoms bond using these orbitals. So if we take a look at hydrogen, for example, hydrogen is a very simple case, right? It's the first element on the periodic table. And so when we're thinking about where that one electron is on the hydrogen, it is in what is called the 1s orbital, right? 1s is just the very first and smallest orbital that we have. The further we go out, the more orbitals there are to choose from. But for hydrogen, since it only has this 1s orbital, there is nothing else, right? It's just that 1s orbital. Whereas if we take a look at carbon, carbon's a little different. Carbon, on the other hand, with its four electrons, has a completely different ground state. So all atoms have this 1s orbital, right? And carbon has two electrons in it. But then carbon moves out into these other orbitals that as we go down the line are a little different. So the 2s orbital of carbon is also filled. Same with a little bit in the 2px and the 2py, but not necessarily the 2pz. And the reason we know this is because of where it sits on the periodic table, right? This 1s orbital is in the first row, and if you think about that, that means that it's not valence. So whenever we were counting those electrons for carbon beforehand, we were actually looking at these four being the four valence electrons, right? Valence does mean that they are in the outer orbitals. And so with this 2s, 2px, and 2py, and 2pz, those are on the outside in that second row, whereas the 1s is on the inside, so it's not valence. So the electrons that carbon is actually using to bond is coming from these further out orbitals. And the thing is, these orbitals directly relate to energy. So we're going to draw a little graph here, and this is going to be related to energy and distance. And that distance is going to be from the nucleus. All right. So whenever we think about this and we're looking at carbon's electrons, the 1s orbital is actually the orbital that is closest to the nucleus, right? And it has those two electrons as we described above. The next closest is actually the 2s orbital, which is sitting about right there. But then those p orbitals, all of those px, py, and pz, they are actually sitting even further away from the nucleus and they're higher energy. And the reason this matters is because that distance can actually be modified based on what we are using when we talk about hybridization. So if our carbon and hydrogen want to bond, we're going to see a little bit of an interesting scenario occur. So our carbon, which we will draw this in blue, our carbon is contributing electrons from its 2s, that 2px, that 2py, and the 2pz orbitals. But as we know, the 2s is already filled. And if we want to bond it to four different hydrogens, we would essentially have one hydrogen, which has one electron in that 1s orbital. We would have the same situation three more times. And we're going to color all these. So we have this red, this orange, this green, and this pink hydrogen. If these want to bond, essentially the electrons from the hydrogens are going to go into those orbitals to share with the carbon. And what this would end up giving us, in terms of an equivalent thing, is that carbon, which originally had these orbitals open to it, 2px, 2py, and 2pz, its electrons are going to stay where they were, and then the hydrogen electrons are going to come fill. So the red electron gets paired up. That's very nice. The orange gets paired up. But then, weirdly enough, the pink and the green would have to fill the same orbital. And this is the problem, right? Because it makes no sense. How can you have two atoms that are filling the exact same orbital? It's impossible because they are essentially trying to get into the exact same space. What would be more sensible, though, is if we were to take this idea and we were actually able to fill the hydrogens in to all orbitals to where they were equal, right? So if we were to take this same idea and instead we had that 2s orbital where it only had one electron and we put that in the pz, then the red, the orange, the pink, and the green could all fill in to pair up with one of the orbitals, and that would be a equivalent mixture. And this is where the idea of hybridization comes into play. Because it's not like you can magically put that 2s electron into the 2pz orbital. Rather, what we see is hybridization occurring. So, what hybridization is essentially if we think about the scenario that we were talking about beforehand, where we have this 2s orbital, and then we have all of our 2p orbitals. And for carbon, right, it has everything chilling in the orbitals as we had seen before. What it can do is, in order to end up with four equal orbitals, it can actually take these and it can essentially blend them. And what it'll do is where this energy is, right? Because I'm still drawing these in terms of energy, you'll actually make four equivalent orbitals that rest in between the orbitals that we saw before. And so these can then each have one electron because they're all the same. And this is the idea of having hybrid orbitals, and these are called sp3 hybrid orbitals. Now they're named this because we're taking one s orbital and three p orbitals, and we're kind of mixing them together. And that mixing creates these nice equivalent mixture of orbitals. So what that actually looks like for us is now if we have those sp3 hybrid orbitals, it doesn't matter where the hydrogens come in because essentially these sp3s are all the exact same so that whenever a hydrogen comes along and puts some electrons into the orbital, they are all equal, which is a good thing. So whenever we actually take a look at methane, here's what we're going to see. So we have our carbon, which is sitting in the middle, and then we have these new hybrid orbitals around it. And they look a little something like this whenever they're attached to the carbon. What you'll see in the book is they have them shaped a little bit like this. And this is, of course, our sp3 hybridized orbital. And what this is essentially showing is the orbital is split into two parts. So if we look at our p orbitals and our s orbitals, right, the s is a circle, the p is sort of an infinity sign where the spot in the center has nothing there. This is sort of a mixture of that, right? Where we have this bigger lobe right here, and then we have this smaller lobe. And that's generated because as you mix the S and the P, they actually have different phases, as we call them, that add and subtract from one another. So if we have those two blue phases adding, they make a bigger blue phase, and then the red phase doesn't add in, so it just stays small. So those orbitals, when we draw them into this carbon, are essentially going to be attached to the different sides. All right. So we'll end up in a situation where we have something like this going on. And the last orbital is a little hard to draw out because it is sort of inside, in and out of the page. But you'll essentially see something like this, where each of these orbitals is sp3 hybridized. And those hydrogens, because remember they come in with that circular s orbital, they will sit over here on the end of these little sp3 orbitals. And this right here, this little bit of overlap is where we see the bond. Okay? And so this gives us a geometry. Because if we were to just bond these things all willy-nilly, it looks a little weird. But whenever we bond them with these sp3 hybridized orbitals, we actually end up with a 109.5 bond angle to where all of these hydrogens are actually spaced out that way, even though it's hard to see in a 2D drawing. But this is a tetrahedral geometry. All right. So when we start talking a little bit about these geometries, just know this is where they come from. It's based on whenever you mix those orbitals, what gives you the equal amount of distribution of where those orbitals can sit. So that being said, let's take a look back at our energy graph. Right, we were talking beforehand about this energy and distance. Right, and we were essentially saying that earlier we have these s orbitals and these p orbitals, and the nucleus is all the way down here. And of course, as you go further away from the nucleus, it increases in energy, and so does the distance. This sp3 orbital is going to sit somewhere like right here. And the reason for this is because you can imagine that the way that we've mixed this was we took one s and three p's, and so that means that this is 25% s, right? Because the s orbital was 1/4 of all the orbitals we mixed, and this is 75% p. All right. But here's the thing. We also have a situation where not all of our orbitals have to mix. So what this means is even though we can end up in this sp3 geometry, Not everything is going to. And the reason has to do with double bonds and triple bonds. So, if we take a look at this Lewis structure of ethene, we see this carbon-carbon bond exists where we have a double bond. And that double bond is actually consisted of something that we call a pi bond. All right? And a pi bond is essentially any double or triple bond. Now, this is a little different from single bonds, right? These single bonds are what we call sigma bonds, right? So anytime you hear me talk about sigma or pi bonds, that is just me talking about single versus double bonds. But the thing that you need to know about these is that sigma bonds oftentimes use hybrid orbitals, whereas pi bonds use p orbitals. So what that looks like is we got to think of these carbons now in a little bit of a different way, right? Both of the carbons are bonded together by both a sigma bond, right? Because this is still technically a single bond. And then the second bond that comes into play is going to be our pi bond. And the reason for this is because if we're drawing out these orbitals, right? So we can see that the carbons have to overlap with these sp3 hybrid orbitals. We cannot have another set of sp3 hybrid orbitals in the same direction, right? You cannot have the orbitals in the same place at the same time. You have to have different orbitals there to be making the second bond. So this bond that we've just shown, this is our sigma bond, right? It is the overlap of those two hybrid orbitals. But for a pi bond to occur, we now have to introduce p orbitals. And so remember when we're looking at p orbitals, they are both um, sides of a node. And so as represented by the node, in this case, we have the carbon in the middle there. But these actually end up coming together in a bit of a weirder overlap where they overlap through space, right? And so those bonds, or those, I guess, lines that I've just drawn, those are what is actually representing a pi bond. And here's the thing, don't mistake this for what looks like a triple bond, because there are two lines there. But what that means is just that these orbitals are interacting with one another, right? They are sharing electrons amongst both of them. So you can imagine it as those are electrons being shared between the two. So anytime we're looking at double or triple bonds, we actually have to keep in mind that it is a p orbital that's being used because only those can overlap through space, right? All hybrid orbitals have to have direct overlap, like we see right here in the very middle of our drawing. That being said, if we take a look at the other bonds that are here, right, because that's just the carbon-carbon bonds, the carbon-hydrogen bonds still act the exact same, right? Where you have the carbons with the hybridized orbitals, and then you have the hydrogens with their little s orbitals that overlap. So this is the actual structure of ethene when shown with orbitals. But what this is actually showing us is if we take a look once again at our idea of blending orbitals, right? We have our s, we have our p orbitals, and we're essentially saying that we need this one, this p orbital to stick around, right? Because this one is necessary for the pi bond between the carbons. So whenever we take these and blend them, this time the carbons are mixing together one s and two p orbitals to give us what are called sp2 hybrid orbitals. Whereas whenever we're looking at that other p orbital, it is still sitting there untouched. So with that being said, we have essentially changed the game. Right now we have an open p orbital where electrons can sit, and we have the sp2 hybridized orbitals. And what this ends up boiling down to is that whenever we look at the structure of ethene, it is not tetrahedral. Rather, whenever we're thinking about this structure, we once again have to think about 3D space, where we have this y direction, this x direction, and this z direction. And based on how we have it drawn, the z direction is currently not represented by hybrid orbitals, right? Instead, it's represented by the p orbital. That is the one that is going in and out of the page that's overlapping to form the double bond. And so for this one, instead of being that one, nice 109, instead to be the most stable, it is actually a 120-degree bond angle. And that makes this structure what we would call trigonal planar. And with that being said, that means that this thing is flat, right? All of this is happening in the same plane. That's the flat part of the molecule. And then above and below that, where these dots would sit, coming out towards you and back into the page, that is where the p orbital would be. But the p orbital doesn't make as much of a difference as atoms do in that direction. Okay? So, with all that being said, essentially keep in mind that you don't necessarily have to mix every orbital. It depends on what you need in order to get good bonding. So, that being said, let's take a look at another example. This is acetylene. And as we can see, it has a triple bond in the middle. And so with a triple bond, it works very similar to a double bond, where the first bond that we're going to form is a sigma bond, but then these other two are both pi bonds. And as we know, based on talking about that example of ethylene, pi bonds are made using p orbitals. So whenever we look at the actual structure of acetylene, for the carbons, it's still true that we need some hybrid orbitals to overlap in the middle to make our sigma bond. And it is still true that we need some p orbitals to overlap for the first double bond. But now the second one, we now have to get an extra p orbital in there because it cannot take up the same position as the other p orbital. So for this one now, we have multiple overlaps. We have the overlap of the orange p orbitals, which is the pz in this case, and we have the overlap of the red p orbitals. And that's what makes our other bonds. In the meantime, the hydrogens that are on the outside still work the same. They have the hybrid orbital coming over and bonding with them. And this is now what we would call an sp hybridized structure. And the reason that it is sp hybridized is because we now have two p orbitals that are being left out and only one p orbital that's being mixed. And so what that looks like in terms of our energy diagram, right? We're going to return to this once again, is like we're saying we have this p orbital that we need for that red lobe, and then we have this one that we need for that orange lobe. So whenever we go through and we do our blending, only one s and one p mix to make the sp orbital, and then two p orbitals are left over for that later bonding. And because of this, whenever we look at the structure of acetylene, we're only using one p orbital, which means that we can only have a single direction being used here. And because of that, we end up with a bond angle of 180 degrees. And so that's why whenever we were looking at these structures, and every time you've been seeing them on the homework and worksheets so far, these are drawn as a straight line because they must be straight as this is a linear structure, right? Linear just meaning that it's in a straight line. So we're going to scroll back up real quick and we're going to take a look back at something that we drew earlier. This right here, our energy and distance graph that we put in earlier. Because now we have two other orbitals to fit in there. We have our sp2, which is going to fall halfway, well, not quite halfway, a little over halfway towards the p orbital, because now this is 33% s, right? It has more s orbital in it, as we would say, more s character, and it is 66% p. Last but not least, we have our sp hybridized orbital, which is going to fall about halfway between an s and a p orbital, not drawn to scale, because this one is 50% s and 50% p, right? Because it has one of each in there. So this is our actual energy versus distance, energy and distance, I guess it is, for these different orbitals. The more s character an orbital has, the closer it is to the nucleus, and the more stable electrons will be in it, which is something that we're going to see in a little while. Now, with that being said, this actually brings up another interesting concept, which is bond length. So bond length is determined by a couple things, right? It's first determined by your bond order. So what this means is bond order is, we're going to dumb it down, just saying, is it a single, double, or a triple bond? All right, that's all you got to ask yourself for bond order. And essentially, if we're looking at a trend for length, and we're talking about what would be the shortest and what would be the longest, it falls in line where the shortest is going to be a triple bond. And the reason for this is the more bonds you add, the closer together those nuclei become. That means our second shortest bond is a double bond, and then our longest is going to be single bonds. That's the easy trend to talk about, right? Because essentially we're just thinking about, oh, how many bonds are there? The more bonds there are, the closer things are going to be. But whenever it comes to hybridization, hybridization plays a role because you can imagine more S equals closer nuclei. Because if we think about that little graph one more time, since the S is closer to the nucleus, that means that if you have more S, it is also going to be closer to the nucleus. So whenever we're thinking about this and we're determining length, right, for hybrid orbitals, we are essentially saying that the shortest must be the one with the most S character. So this would be our SP hybrids, whereas the longest are the ones with the most P character. So this would be our SP3 hybrids. And that means that SP2 falls right in the middle. And why this is important is because it describes something that we can't describe necessarily without using hybrid orbitals. And the reason I say this is we can look back at the structure of acetylene and we can talk about the bond lengths here, right? We know in general that looking at these two carbons, they have a really short bond between them, right? Because triple bonds are short. But then we can also say that the CH bonds are shorter than normal. And the reason we can say this is because we can compare it to something like methane, right? Good old CH4. And when we're comparing it to methane, and if we were to call this sort of normal in this case, We can say that the CH bond in acetylene is shorter than the CH bond in methane because the CH bond in acetylene is made of an sp and s orbital, right? The sp comes from the carbon, the s comes from the hydrogen, versus over here in methane, it is an sp3 in an s orbital. And as we see above, since sp has more s than it does p, that means that it is shorter than an sp3 orbital. And so the book goes into this a little bit and talks kind of about how all of that works and gives a little bit of a good explanation, a good way to think about it. I recommend taking a look at it. But that's all we're going to talk about bond length for now. It will come back later, though. So, that being said, we have to think about now some examples of how hybridization occurs and what it actually looks like in a real molecule. So the first molecule we're going to look at is acetone. That is the structure here. And so what I'm going to do is I'm actually going to convert it to a Lewis structure to help us better see what's going on, right? So if we were to look at this in terms of a Lewis structure, we have the three carbons that are bonded to one another. And the carbons over on these sides are bonded to hydrogens, right? Because they're both CH3s. Because remember, in bond line structures, we imply those. And then the carbon in the middle is bonded to an oxygen that has two lone pairs on it. So looking at these, we can say that these carbons on the end, right? They have all sigma bonds, right? They have three to hydrogens, and then they have one to a carbon. And that tells us that if it's all sigma bonds, there's no free p orbitals, which means that it is sp3 hybridized. Versus if we take a look at the carbon over there, it's the same, but the carbon in the middle is a little different, right? It has sigma bonds that sit between it and the other carbons, and it has one sigma bond that sits between it and the oxygen, but then the other bond that sits between it and the oxygen must be a pi bond, right? It has to be made of a p orbital. And remember, it's because orbitals cannot be in the exact same space as one another. So that means that this one in the middle must have one p orbital, which means it is sp2 hybridized. But the question now becomes, what about the oxygen? Because if we take a look at the oxygen, yeah, it has a p orbital, but what are the lone pairs going to be doing? Where are they going to sit? And so if we take a look at the drawing of this, right, we can say that, all right, we're going to draw in all of our sigma bonds for all these carbons, and those are going to be sigma bonded to all of the different hydrogens. So here we go. Those are all there now. And then we have the star of the show, which is this carbon-oxygen bond. So there is, oops, I'm going to draw the oxygen red to make it a little more obvious. So there is our sigma bond. And then we also have to have a p orbital that is shared amongst both of them, right? And this is overlapped to make that pi bond. So the question is, what happens to those lone pairs? Well, as a matter of fact, the lone pairs actually make no difference because the lone pairs can exist in hybrid orbitals. So what that looks like is alongside the oxygen having these p orbitals, it also has these sp3 hybridized orbitals. And in both of them sit, or sorry, sp2 hybridized orbitals, and in both of them sit those electrons. So these are still in sp2 hybrid orbitals. And the reason is because it is more stable for them to be in the sp2 hybrid orbital than it is for them to be in a p orbital, right? And the reason for that is once again, we're looking at this energy graph. This thing is coming up all the time, right? The energy and the distance are intertwined to where as you increase in distance, you increase in energy. And so p orbitals are inherently less stable for electrons. And so because of that, if they can mix to form these sp2 hybrids, rather than staying as p orbitals, they will. So in the end, what that means for our drawing here is that the oxygen is indeed sp2 hybridized. And those electrons just sit within an sp2 hybrid orbital rather than a p orbital. So we're going to do one more example, and then this will be the end of it until we talk about what happens next with this subject. And so we're just going to do one more example that looks like this. So taking a look at this one, we're going to do this one in bond line, right, to give us a good idea of how this works in bond line form. Looking at the carbon all the way on the left, we know that this one has three bonds that are not shown, all the hydrogens. They're all single bonds. So that means that it must be using only sp3 hybridized orbitals because there's no need for a p orbital there. For the second one here, we see that there is actually a pi bond between these two carbons. What that means for us is those other two hydrogens not shown are both sigma bonds, but that does mean that we only are looking at an sp2 hybridized one because it needs one p orbital that is not mixed. Same with the other carbon down here. This is sp2. This carbon over here has all single sigma bonds, so that means it must be sp3. Then we have this carbon right in here. So for this one, we see that it has the sigma bond to the nitrogen, but it also has these two pi bonds. And so those pi bonds each take a p orbital. So that means we need to leave two p orbitals unmixed, which means we're looking at an sp hybridized carbon. Last but not least, the nitrogen on the end. It does have a lone pair sitting here, but that doesn't change anything because as we know, those can also go into sp orbitals. And as a matter of fact, it only needs those two pi bonds for the p orbitals, meaning this is sp hybridized. So, to summarize sort of what we're looking at whenever it comes to hybridization, is you always have to ask yourself the question, how many p orbitals do we need? Right? Because essentially orbitals like to mix because it makes more stable um, orbitals out of dropping the energy of the p orbitals despite raising the energy of the s. So orbitals love to mix. You just have to ask yourself the question of how many p orbitals does an atom need? And to figure this out, you are looking at pi bonds. And then the other thing that you need to keep in mind is the hybridization determines geometry, right? It determines how things are shaped. So when we're looking back up at this structure here, every time we label something as sp3, we are essentially labeling it as tetrahedral. Every time we label something as sp2, we are labeling it also as trigonal planar. And every time we're labeling something as sp, we are labeling it as linear. And so that's the idea of hybridization. Now, that being said, next time we're going to talk about how hybridization can get a little less simple when we look at how resonance actually interacts with hybridization. See you next time.